All right, please welcome Elena Rasia. She graduated from the astronomy department of Padova University in 2006. And after a brief postdoc at University of Bologna with Stefano Ettori, she moved on to the University of Michigan, where she was a Chandra Fellow. She was a Michigan Society of Fellows Fellow and was supported for by a three-year award by the NSF. She returned to Italy with a Marie Curie Incoming Fellowship in 2015 and obtained a permanent position at the Observatory of Trieste 2 years after. Since her master's thesis in 2003, she's been working on numerical cosmological simulations carried on with the code Gadget. She's part of the steering committee of the 300 collaboration, chair of the hydro simulation working group of Checksmate, and an active member of the Trieste Munich collaboration of the development of Gadget 3. So thank you, Elena.
Thank you. So thank you for the introduction, for the invitation, and for the opportunity given to me to talk about this project on barium fraction evolution. The project was started with a master student in Trieste, Roberta Tripodi, and now we are wrapping it up and hopefully will be submitted in the early summer. So the goal is to study the barium fraction, and particularly how we can model the barium fraction evolution, looking at simulated galaxy cluster taken from the 300 collaboration. The barium fraction is one of the most used tools. To do cosmology with a galaxy cluster. And the reason behind that is quite simple. So if we are able to measure the barium fraction within cluster, that is defined as the ratio between the mass of all the barium components or the baryonic components over the total mass of the cluster, we think that this barium fraction in cluster is representative of the cosmic barium fraction. And this assumption is motivated by the fact that in most massive cluster or redshift 0, the material that we found within them is originated from a wide region of the universe of order of 10 or even 15 megaparsec. And so we think that the cluster can represent quite well the overall cosmic barium fraction. So once we know the baryonic density parameter from the Big Bang nucleosynthesis or from the cosmic microwave background studies, we can automatically obtain the matter density parameter of the universe. This equivalence is something that can be checked quite easily with simulations, because in our simulated universe, we know a priori the cosmological parameters that we use to simulate our universe. So we know the first ratio that is shown here in red, and we can then measure what is the barium fraction in our simulated cluster to see if these are this barium fraction is really representative of the cosmic barium fraction. So this game has been played by quite a long time, and what has been seen in simulation is that the equivalence is in place only when we consider a very large region of the cluster. So optimally, the virial radius that for a Planck cosmology is of order of over density of 100. But as long as we reduce the virial radius over density of 200 or even 500 or 2500, the equivalence is no more in place. We have less baryons within cluster, and we call depletion factor the difference between the cosmic value and the barium fraction that has been seen in cluster. So simulation are a wonderful tool to see and to model this depletion factor in the barium fraction over a wide mass range and also over time. So towards the end of the talk, I will focus a little bit more on the gas fraction. So the barium fraction, as you see here, is it's composed by the gas fraction plus the stellar fraction. Measurement in X-ray are mostly devoted to the gas fraction. So I will show some comparison. And whenever I will do that, I will correct and I will take all the observational data to the cosmological model that we use inside our simulation. So this work is based, as I was saying before, to the 300 in the 300 simulation. These are resimulated region of the 324 most massive cluster identified in a parent dark matter only simulation that has a gigaparsec, 1.5 gigaparsec as a side. So starting from this large cosmological volume, we selected the most massive cluster and we select a region around them and we resimulated this region at high resolution and with the inclusion of baryons. So the advantage of this simulation is the incredible high statistics of massive clusters. So we have more than 300 objects at redshift 0 with mass above 6×10 to the 14, and we can trace back their evolution up to higher redshift. The specific work is focused on 10 different redshifts from redshift 0 to redshift 1.3. And the cosmology used in the simulation is a Planck cosmology. The resolution of the gas particle is here in the bottom of order of 10 to the 8th. I want to stress that in the world, so this is the second largest suite of massive cluster, second only to the Magneticum box 0. That is a whole cosmological volume of a bigger size, is over 2 gigaparsec as a side. However, the resolution of that simulation is 10 times worse. So with these 300, we are able to reach a higher redshift, so to go down in the mass range that we want to probe. Another comparable simulation is Maxis, that also has about 300 cluster, but also has a smaller, worse resolution of order of 2-3 times. So just a brief comparison with data. I will come back to other comparison later. Here we reported the gas fraction and the stellar fraction separately in the presentation paper by Cui of 3 years ago, the presentation paper of the simulation suite. And you see that in the region that is probed in this work, so the most massive cluster, so there is a good satisfactory agreement in both gas fraction and stellar fraction. The barium fraction that is made by the sum of these two is shown in this plot where we extended the comparison to different works. And we see that the simulation at redshift 0 are quite well represented in the data. So just pointed out these 3 observed clusters with a very high barium fraction that is even above the cosmic barium fraction, here shown by the horizontal line. So these are 2 objects, 2 above cluster that are part of the supercluster, the Eurologian supercluster, the Shapley supercluster, and another object about 2319 that is known to be a merging system and very complex system. So it's likely that the measurement of either the gas mass or the total mass of these 3 objects can be biased, and this is a good explanation why the barium fraction is so high for this observed object. So the sample, as I was saying before, is built up by 300 objects, more than 300 objects that are followed across the time from redshift 0 to redshift 1.3. And we focus on the 3 different overdensity. R200 is what is considered the boundary of the cluster most of work. R500 is a region that now is well probed by X-ray observation, while R2500 is more in the central region, just outside the core of the cluster, and is representing what we observe really just in the inner part of the system. So all these images are showing the baryon fraction of this 3 over density in relation to the cosmic baryon fraction, again showing with a solid line here at value 1. So already here you can see what I was mentioning before, that if we stop the measurement at a very large radii, so containing the entire volume of the cluster, the depletion factor, so this mismatch with what we measure in the cosmic baryon fraction, is only of order of 5%. But when we reach the more internal region as an R2500, the depletion is much larger. And also there is a quite a larger variation cluster to cluster. So the 4 different colors are simply showing 4 different redshifts extracted from the original sample. But again, we consider all the 10 of them, and it's just to show how they appear all together. So the idea now is to look at each single subsample, so at fixed redshift, and to look first at what is the best formula or model that we can use to match and to relate the baryon fraction to the total mass of the system. So we start from the most immediate expression, so simply a power law. The gas mass and the stellar mass are assumed often to be described as a power law, a function of the total mass, so also the ratio can be represented as a power law. In the plot here, in the left side, I'm just reporting the parameters of the power law description for all the individual redshift. And as you can see, most of these parameters are quite constant and regular, with the only exception of the normalization when the measurements are done in the centermost region, R2500. And the normalization that changes with redshift with these dependence. However, if you remember the plots I'm showing before, and here instead of showing all the 4 redshift, I'm just speaking at 1 redshift around 0.6. The clusters are not really distributed as a power law. They're not a line in the logarithmic plane, but you see that there is more curvature into the points. And this was also shown in other simulation, where here they are showing only the gas fraction, where clearly there is not a linear relation between the 2 logarithmic quantity. So another description that we used was taken by Stanek paper, where they introduce a parabola in the logarithmic plane. So the parabola is able to describe the curvature and potentially also this flattening at the high mass end. So again, here is just the evolution of all parameters, but I want to stress is the plot down here, where we report the differences of the goodness of the fit when we use a power law or when we use the logarithmic parabola. And you see all the differences positive, meaning that the logarithmic parabola is a much better description of the distribution of points. And we will see that better by looking at this specific redshift, where we show all the fitting that we have tried. So first of all, the power law, and as you can see, the power law, the best fitting power law to this set of data is experiencing 3 different problems. So it's not reproducing the drops that we see in the baryon fraction at the lowest mass hand, is not reproducing the flattening. So you see all these 6 redshift mass being, they have most likely, they have all the same identical baryon fraction. And it also does not represent the curvature that is present here in the intermediate mass bin. If we instead use a parabola is a much better representation of all the points, and as a clear result, the chi-square, so the goodness of the fit, decreases from 1.9 to 1.1. So a parabola is much better at describing all the features that we are seeing, so flattening high mass and the decrease at the low mass end, and the curvature that is present here. We also employ a different function that is similar to what Alexei was using in his paper of 2009. However, we use that in the logarithmic plane, so will be a logarithmic of a logarithmic. And this is shown for the same redshift in the dark green line. So the logarithmic is also a good description of each individual subsample at the fixed redshift. So the chi-square is similar to the one that we obtain with the parabola. The only thing that we notice in each redshift bin is that it does not really reproduce the flattening at the highest mass hand, because the logarithmic is slowly, most slowly approaching the asymptotic behavior. So at this point, we have studied each subsample, a different redshift separately, and we want to put them all together, because unfortunately, when we have an observational sample, we don't have the luxury to bin the cluster in redshift bins. Above redshift 0.6, there are few tens of objects, and they span between 0.6 to above 1. So what we want to do is to put together all the redshift and to see what description works better when we include all of them all together. So the idea is to use a function, either the power law, the parabola, or the logarithmic, that is as a constant shape, but is allowed to vary in redshift for the normalization. And we consider both the dependence of 1 plus e and the dependence of ez, the cosmological evolution. The expression is shown here in the bottom. So what we notice when we do this game is that the logarithmic description, even if is does fit well each individual object, when we put them all together at a different redshift, is failing to reproduce the spread that we see in the central region in the lowest mass cluster, because the logarithms tend to drop very rapidly. Instead, the parabola does a better job down here, but also does a better job at a higher radius, a larger radius, lower over density in the higher mass end. You see here the logarithmic is again increasing, so it still hasn't reached the flattening that is reached much later, while the parabolic function is well representing all the objects of the high mass cluster. So the point here is that when we have an observational sample, we are putting together objects at low redshift, and they are mostly massive redshift, but we are trying to include more and more objects at high redshift. Even if you pick the highest mass in the highest redshift universe, you, however, are already in the declining phase of the Barium fraction. So you can see for these selected redshifts, so 0.6 and 1.3, that the drop of the Barium fraction happens already at 3, 10 to the 13, 4, 10 to the 14 at the intermediate redshifts. Is already there at 3 and 2, 10 to the 14 at the higher redshift sample. So it's very likely that when you go to very high redshift, this object will be included in your final sample. And so it's important to use a description, as we are saying, that parabola that is more tracing the drop of the barium fraction for the smallest object. So now in the remaining time, I want to focus a little bit more on the gas fraction. So as I was saying before, all our work was focused on the barium fraction, which is the sum of the gas fraction and the stellar fraction. The stellar fraction is extremely difficult to measure. So there was a recent paper by Svetlana on Abel 133 that she made an extremely careful census of the stellar population and the stellar mass within the cluster, but such a detailed paper is not easy, such a detailed investigation is not easy to be reproduced in a very large sample of cluster. So often what is done from the observational point of view is from X-ray studies to study the gas fraction, and then maybe to use a stellar fraction formula that comes from other works like the Gonzalez 2013. So here I'm focusing a little bit more on the gas fraction. In the slide, I'm just want to compare with a paper by Adam Mans, also a paper that had a focus to constrain cosmological parameter, was based on 40 objects, all very massive, temperature above 5 kV. And in this paper, it suggested that if we use a shell around 2500, between 80% and 1.2 R2500, so the gas fraction measured in that shell is more precise and has a cluster-to-cluster scatter that is reduced with respect to the gas fraction that is measured within 2500. So we check this claim in our simulation, and we confirm that is true, meaning that the scatter in the shell is 10% lower than the scatter in the whole sphere at 2500. However, when we do the same calculation in terms of the barium fraction, so when we consider also the stellar fraction here, we don't see a very large difference between considering the shell and considering the entire sphere. So the reason being because there are two separate phenomena that are happening and that are important for the gas fraction. So the first one is the AGN that is acting a very high redshift and is pushing away baryons from the galaxy at high redshift. If that happen in a region that is in a poor environment, that single galaxy will develop by redshift 0 in a small mass objects below 10 to the 14 or around 10 to the 14. And so the depletion that we see in the barium fraction is caused by the AGN that expel a lot of gas early on. If that instead is in an enriched environment, what we have that the baryons are retrapped, especially if we consider a large radii, they are retrapped inside the cluster, and the division between the gas and the star component happen because of in simulation happen because of subgrid processes. So we have all the baryons at disposition. The baryons, some of them can cool down, the gas can cool down, can form a star. And typically when you start with the same amount of baryons, so you can have a situation where you have more gas mass associated to a lower stellar mass, and vice versa, you can have a low gas mass associated to a very high stellar mass. The ratio between the two components basically depends on the efficiency of the star formation and also the efficiency of the AGN to dump and to block the star formation. So another comparison with data and other simulation focus on the gas fraction at this time are 500. So on the left, comparison with different simulation. I omit the comparison with simulation that are done exactly with the same code. You see the 300 that are here in this light purple agree quite well with the Sea Eagle simulation, while they clearly are much more gas rich with respect to Cosmo Owl or the Bahama Maxis that are down here. However, both of these simulations were actually produced and calibrated to reproduce the gas fraction in the group regime. Another comparison with data focus again only in the gas fraction and not the Barium fraction. So all the color point are data, our clusters are the light pink circle on the background. And you see that more or less for the massive system, we are reproducing, we are in agreement. We cluster this, but still there is an indication that and in the low mass regime down here, we might be a bit more gas rich than what the observation are trying to tell us. Everything is, however, well within the spread of the observations. And this is probably the most noticeable point. The biggest difference between the observation and simulation is the scatter that we have. This can be due to two different problems. So well, first of all, observation, the measurement of the gas fraction can be affected by the total mass measurement uncertainties and maybe presence of clumpiness if they are not very detailed. And in simulation, I would say that the problem is that maybe we have still too simplistic subgrid physics modules. So as I was saying, even if the Barium fraction is quite robust in the simulation, when you go to distinguish between the gas and the stellar fraction, the physics that is implementing in the simulation is quite important. And maybe they are, the models are too simple, and so we cannot really reproduce the variety of situations that are present in observed cluster. One problem, for example, that we have is still a very high redshift. So this is a comparison between some observation done in protocluster region, and the observation are the color point, and the simulation that are the gray points down here. And what we are comparing is what is called the main sequence, so the star formation rate versus the stellar mass of the object. And you see that the observed protocluster can have a star formation rate that is never reached by our simulated protoclusters. And this problem is not only affecting our simulation, but it's common to all simulations that have clusters within them. Another way to see these problematics is to look at a slice in the stellar mass and to plot the distribution of star formation rate in this stellar mass bin. So observational telling us that on top of the normal distribution of galaxies, so that is defines the main sequence, this is these extra components of the sub-millimeter galaxies that are very difficult to obtain in cosmological simulation that contains galaxy clusters. So this is a comparison with the Magneticon and the Dianova. They completely miss this high star-forming object. Some improvements have been done recently. For example, this paper shows Lovell 2020 using Gizmo and Simba. Then the distribution of sub-millimeter galaxy can be reproduced. However, this box is still too small to contain a large number of clusters. And the difficulty now is try to see if we can simply extend what has been done here to a larger volume and to reproduce the same feature in protocluster region. But this is just a detail, a warning about the fact that our simulation of cluster are still not really reproducing all the variety of situation that we do see in observation. But going to the conclusion of my work, so I've been shown that cosmological simulations, such as the 300 cluster simulation, are well suited to investigate the barium fraction depletion. So this difference, this offset that there is from the barium fraction measuring clusters and the cosmic value of the barium fraction. The barium fraction can be described as a power law, but only if you limit at the most massive cluster at a close redshift. Whenever you want to include a lower massive system in your sample, or you are going to redshift around 1, it's better to describe the whole distribution using a parabola instead of a simple power law. Then my final warning was that concerning that while cosmological simulation are a good tool to investigate the barium fraction, if we want to break down between the stellar fraction and the gas fraction, there might still be problems that need to be solved. Thank you.
Thank you, Elena, for a great talk. We are a bit over time, but we'll take a couple of questions. And if folks want to stick around, we can have questions for both speakers. Okay, I see a raised hand from Bill and Christine.
Hi, thank you for the wonderful talk. I had a question about your early on to the later slides. It looked in the beginning like you were getting good agreement between the baryon fraction in the gas and the baryon fraction in the stars, and that was working well. Did that mean that you're getting a good model for your feedback for the galaxies, that you really believe you understand how that's working to get that balance correctly?
Yeah, so I was, when I was talking, I was focusing more on the high mass regime because it's the what we use for this work. However, in this simulation, since the Lagrangian region that we use, that we resimulate are large enough to contain also other groups, we can also compare with small mass system. And here there is an indication that the overall stellar content is a bit lower than what has been measured in observation. That said, again, if I go back here in the most massive regime, the BCG, the mass of the BCG, sorry, I skimmed through the slide. I should have a slide here. The mass of the BCG that we obtain is quite well reproducing what was observed and shown in Kratz of 2018. So the stars are the observation, the mass of the BCG at different radii, and all the lines are 3 different simulations, and what we are using are the blue points. So I would claim that the feedback in most massive object is okay for this object. Probably the overall history is also okay, meaning that the average behavior of our simulated cluster can reproduce the average behavior of observed, but we are still not reproducing really the variability or the spread of situation that we have in observed cluster.
Thank you.
Very nice.
We have a question from Erwin Lau.
Hi, Elena. Thanks for a great talk. So I was wondering, when you talk about the baryonic effect is mostly affecting the R2500. So I guess if you really want to do, say, cosmology with gas fraction, we can just go further away, say R500.
Yeah, we still look at also the 2500 because there have been work in literature that they focus mostly on this inner region. But yeah, you're perfectly right. I mean, as closer we get to the BCG, as stronger it is the effect of the AGN and the pushing away of the baryons from the AGN that happened earlier on. And so the depletion is stronger as we get closer to the center. Yeah.
Yeah, and also you mentioned that you're still not able to reduce the variability of gas fraction So, and you mentioned that clumpiness could be one explanation. If you try to see, like, compute the clumping factor in the summation and see if that can at least explain some of the range of the variability in the observations.
Right. So, well, the overall clumpiness level is comparable to what has been observed, but clumpiness is mostly, I mean, smaller within R500, grows up afterwards. I was mentioning that especially for the observation up here. So at least these three clusters that I went to check exactly which objects are there. So as I was saying before, two are in a supercluster, another is an emergent system. So it might be that the clumpiness affected the observational measurement, so the derivation of the total mass of the system. So if you have clumps, so the gas density is shallower, so the derivative of the gas density is lower, so the total mass associated with this object can be lower, and therefore the fraction where the total mass is in the denominator might be higher. So I did not separate the simulated cluster between so in terms of their clumpiness, because clumpiness is not affecting the simulation measurement, because in any case, we take everything within a certain radius. So the problem of clumpiness is that the derivation that you can have from an observational point of view, if there are clumps and you're not able to detect them, you might have a wrong estimate of the slope of the density profile.
All right, we have Alexei with a question, and if anyone's been holding questions for Marat, after him, would this be a good time?
Okay. So Elena, on one of your plots, you had the baryon fraction as a function of mass, and it shifted with redshift to the left. So yeah, this one. So did you look at what precisely is the redshift scaling?
The redshift, say?
Redshift scaling of that relation.
Yeah, I reported only in the conclusion. So is in any case is very mild. So this factor here referred to this parabola that we are using is extremely mild for R500, is a bit larger for R2500.
Is it entirely empirical?
Yeah, I mean, yes, based on simulation, yes.
So
well, also the something that I didn't stress, also clearly to use a parabola or a logarithmic is absolutely entire empirical, doesn't make I cannot see any theoretical explanation why this functional formula should be used.
Yeah, so just a suggestion, in our work we we looked at Kravtsov and Daikin simulations, and looked at the scalings. So it seemed what seemed to work is when you scale the cluster mass by the m star, where m star is a non-linear mass scale at that redshift, and then all these relations just lined up. So you can try to see if they line up, and then you might get a better handle on the trend.
Yeah.
All right. Are there any further questions for either speaker? If not, let's thank both of them for a couple of great talks. And there's still plenty of time on the sign-up sheets, which are linked from the emails reminding everyone of these talks. Thank you all for coming, and hope to see you again next week.
Thank you.
Thank you.